your rolling argument. So we'll just play this.
Alright, time for Draftscience.com. Video presentation, debate physics also, where you'll find playlists, so to speak, of these hopefully short videos on single subjects, essentially refuting the kinetic energy theory. So today we'll talk about friction and rolling things, and this isn't really a cited experiment directly, but it's indirectly cited when you ask physics to show you it taking 4 times the fuel to go twice as fast. They'll often talk about braking distance or rolling distance instead of just showing you what they should be showing you, and they can't because it doesn't happen actually. Alright, so this is basically the same as the gravitational argument. You could just drop these things instead of roll them, and you're basically just saying you're going to use friction to take the energy out. So the thing has some kind of energy, whether it's momentum or kinetic energy, it doesn't matter. It has a mass and a velocity. Whether you square things and have things, it's not going to change anything.
Right, it's interesting there that you said it doesn't matter whether it's kinetic energy or momentum, because obviously we can test this out. You know, you're just making a claim. You're not showing any evidence to support it. You're just drawing it on a board and saying it's so. You know, which isn't really very scientific, is it? It's, you know, if you're saying it works this way, then you would have to show some evidence to support that. But drawing a picture on a board and saying, well, asserting that it works this way is not evidence. So, like I say, we probably can test this out. You know, that this is the thing, you're claiming it, but you can scientifically test these things.
It's a mass and a velocity, and you propel it. So this has twice as much of that. Okay. And in terms of it has twice as much velocity as you're using the same mass, okay, and you want to roll them on a surface. Fact is, the one that goes twice as fast will actually go 4 or even 5 sometimes the distance, okay, you'll roll much further, okay.
Right, so that isn't a fair comparison. You know, if you wanted to test this thing out, you know, is friction linear? Taking 2 masses, giving one velocity and 2 velocity, obviously, clearly, you know, you give them different amounts of energy. So if you give them different amounts of energy in, you're going to get a different amounts of energy out. So that wouldn't really be a fair comparison.
Okay, then twice the velocity. Now to some, you know, platypus duck kind of comparison, you could say, well, that seems like, it sure looks like 4 times the energy. Look, it went 4 times as far. Well, it doesn't really need 4 times the energy to do that because of the advantages velocity creates. So in this circumstance, you're using gravity to apply your friction. Okay, you're taking the energy out using a gravitational process, and the gravity.
Yeah, gravity's ever present. You know, in any experiment we do on Earth, we're pretty much, you know, bound by gravity. So I don't know where you're going with that one.
Does in fact have rules about velocity. The faster you go through gravity, the less it's going to affect you. It's a time-dependent force. And the fact is that this rolling distance and this rolling distance will have a 2-to-1 relationship. This will only take 2 units of time. So even though it's 4 units of distance, it'll only take 2 units of time. This is only 1 unit of time. And effectively, just like in gravity, this part of the voyage, this velocity, will be exactly the same as this one here. You'll reach half your speed here. 3/4 of the way down the track is where you'll end up going half the speed. And that's the real giveaway that this isn't linear. That is the amount of friction, okay, the amount that
right,
is
again,
being
you make
taken
that,
by the ground, the amount of energy the ground is taking.
You make that claim it isn't linear.
From you. You're consuming the energy. We're applying a force against something. We're allowing there to be an electrical contact, is how you could understand it. We're allowing contact, and we're going to pull the amperage or the wattage out of something because we've improved the contact. And the faster you go, the less contact you have with the surface. So you're losing less per foot.
Right, the faster you go, the less contact you have with the surface. You really got to think about what you're saying there. Because if you're not contacting a surface, you're not accelerating. You can't. Friction, you need friction to go faster, to accelerate. I mean, have you ever seen a Formula 1 car? You know, they have like an inverted wing on the back of the car to force it down, to press it in, to create friction to drive the car at super high speeds. You know, this, if you're not contacting the ground, you've got no friction, therefore you've got no acceleration. You can't go faster if you're not contacting the ground.
And then you lose more the slower you're going. Now, obviously, this is a very nice linear curved line, and I'm not drawing it as a curved line because your velocity is decreasing based on a curve, and then this velocity is based on a curve, but the two curves are different. This curve is more dramatic than this curve. You're losing more energy here than you lost in this whole section here. So this whole section, this whole unit of time, you lost the same amount of watts. Okay, if we're going to turn it into something else to understand it, you pulled the same wattage out of the rolling object here that you pull out here, because there's more friction here. There's more weight on the ground.
Again, you're making that claim there's more weight, there's more friction. How are you demonstrating this, apart from drawing a picture?
Because you're moving slower per foot, so that means you're losing less per foot over this distance. So it's simply just back to Galilean 500-year-old physics that can be understood, that there's rules to everything, and the rules to losing your energy to something means if you have to make sure it's linear before you claim it's linear, and this isn't linear. That is, it changes dramatically as you go.
Right, again, you're saying it's a claim and it's not evidence, but you're making a claim to the contrary with no evidence.
Slower and slower, more and more energy is pulled out. So I could draw these lines a little more accurately by you start off, the faster you're going, the less you're losing. The slower you start going, the more you start to lose, until you finally get to the end where per inch or per foot, you're losing a lot of energy per foot. But by time, it's all the same. This is the same as this. Two units of time. Okay, so frankly just saying to you that this is a time-dependent force. It only takes twice the time. There's only twice the energy that you're pulling out by gravity. And again, the fact that it's half the speed here instead of here in the middle is what demonstrates that it's doing the same thing that gravity does. So you have to use some other kind of friction that isn't gravity-dependent if you want to fairly...
Right, some other type of friction that isn't gravity-based, right? I'll just, build an anti-gravity unit and try that out. What the hell are you talking about?
Or evenly consume something's energy. You have to apply some other force that isn't time dependent. Some force that is in fact
another force.
Or it just depends. It's going to do the same thing each time, like bowling pins or some other thing. Bowling pins aren't perfect because they stand up in gravity, but anyway, some other mechanism to pull the energy out where it isn't dependent on that mechanism changing as you change the amount of time. All right, so it's really not an argument for the kinetic energy.
Clear as fucking mud, that. Like I say, we can test this out. You're just making a claim here. You're just drawing on your board, saying it works this way. You're not no evidence to support your claim, no experimental evidence, just a claim.
Energy theory. The fact that it rolls 4 times as far means nothing in terms of figuring out how much energy you pulled out, because you pulled it out differently depending on how fast it was moving. It's as simple as this scale, and you can just logically understand the faster you go across the scale, the less you're going to weigh. And the slower you go, the more likely it is you will weigh your full weight. So as soon as you go fast enough, okay, where you're going to weigh something less than your actual weight, it'll get less and less.
Right, so all I can surmise from what you're trying to claim is that faster, lighter objects incur less friction than heavier, slower moving objects. I think that's the crux of your argument.
The faster you go, that should do it. So it won't be a refuted argument. Nobody will say anything to debunk it or refute. That's how it does work.
Right, so after listening to your arguments, obviously we need to devise some sort of experiment to test this theory out. So, obviously with it being a rolling argument and, how much friction these things incur, I think it'd be a good idea to use a cart, a wheeled cart, low friction, keep it quite substantial, so have the cart weigh 2 kilograms, add a further 2 kilograms, so the heavy cart's 4 kilograms. We can then, send that cart on its merry way at a speed, and then we can reduce the weight by half, so half as massive cart, and see how that fares when we launch that. But in your video you said it doesn't matter whether it's momentum or kinetic energy. Well, that's a good thing, because we're trying to measure how much energy is taken out of the system due to friction. If friction is linear, will it draw the friction out? Will it draw the energy out through friction at the same rate? So say we launch the heavy cart, the 4 kilogram cart, and that goes like say 10 mile an hour. And then we would say, well, we'll reduce the weight, and take it down to 2 kilograms. And obviously we want to make it go faster. So if we said we want to make the lighter one go twice the speed, then we've got a bit of a problem there, because yes, the momentums would be the same, but the energies would be different. So to propel this 4 kilogram cart at 10 miles an hour takes an amount of energy, but if we wanted to propel the 2 kilogram cart at twice the speed, we would have to add more energy for that to happen. So if we were to test that under those conditions, obviously the 2 kilogram cart at twice the speed has received more energy to start with. So if we were to be testing for energy, clearly this one, this 2 kilogram cart at 20 mile an hour would have an advantage, because we've had to put more energy into that to get that to the same momentum. So that would be not a fair test, because clearly this one's more energetic, and if we put more energy in to start with, we would obviously expect to see more energy out. So this would be an unfair test. So what we're looking at is we want a cart that's, we can reduce the weight obviously by half, we can make it lighter, but we want the same energy input into both. So the best way I can see of doing that is obviously attaching a spring, launching it via a spring. So there's a set amount of energy going in, and then we take the 2 kilogram, take the weights out, launch 2 kilogram cart with the same spring. So each cart possesses the same amount of energy when it's launched, and therefore we've got an even keel there. We've got a heavy mass going slow, and we've got a lighter mass going faster, which I think meets your criteria. What you're saying is a lighter, faster thing would incur less friction. So yes, it would only be roughly travelling at 1.4 times faster, but that is still faster, and obviously it's half of the weight. So I think that meets your criteria of a heavy mass moving slow and a lighter mass moving faster. Like I say, we've got the same amount of energy in both, so therefore when we are looking at that energy being drawn out due to friction, if there's the same energy in, then when we look at how the energy is taken away from both objects, it's a fair test, because they both had the same energy to start with, and that will give us a good indication of whether or not there is energy being lost due to friction for a slower, heavier moving object, or there's inversely that a lighter, faster object incurs less friction. So either way, we should see some sort of discrepancy in how the energies removed from both of these when they're launched. So just to clarify in terms of, momentum and kinetic energy, just say this is a 2 kilogram cart and this is a 4 kilogram cart, and we need to put some energy in to make these things move. So if we were to put, say, that amount of energy into the 4 kilogram cart and that made it go 10 miles per hour, and we put the same amount of energy into this one, this will only go 1.4, which would be 14 miles an hour, not the 20. If we wanted it to go 20, we would have to put more energy in, and obviously there you can see that if we put more energy in, then we would expect to get, if we were, say, these were cups of water and you were pouring them out at the same rate, obviously this one to go 20 miles an hour has more energy to start with, and so if we were to pour these both out at the same rate, obviously this faster, lighter one at 20 mile an hour would have, would go further, would go faster, would have more energy to start with, so therefore we would expect to see it on the way out. So the reason I'm suggesting we look in terms of energy is because we're keeping the amount that we put in to the system for both carts the same, and therefore when we try to, draw this energy out and see how that works, that we've got an even amount of energy in both objects, and therefore if we're to draw it out, we can, we've got a proper, like, level playing field type of thing, as what they say. I don't know, but it's a more, it's a fair test where, if, like I say, if we go with momentum, we've clearly got to put more energy into this one to get it to go twice the speed. It would have the same momentum, but momentum isn't energy. This, you need to put energy in to give something momentum. They are different things, whether you want to believe it or not, they are. So, and like I say, in your video, you did say, as long as we put something in, whether it's momentum or kinetic energy, and like I say, we're trying to draw out the energy due to friction, so it makes sense to put the same energy into both carts, launch them, and see what happens. Right, so we've got his carts, and we're going to launch them with a spring, so same energy in, and see how much we get out. Obviously, the lighter cart with the same energy being put in is going to go a faster speed. So just say that one's going 14 and this one's going 10 mile an hour, so 14, 10 mile an hour, so one's going to go faster than the other. Obviously, because they're accelerated up to that speed, they are both going to travel, different distances. So you could say that one's, a big distance, this one's going to be a smaller distance. So again, if we were looking at that, we're going to think, well, yep, this one's going faster and it's going further. This one's going slower and a shorter distance. So that doesn't really tell us a lot. We can't really, compare that as such, as it doesn't shout anything out at you. They're clearly different, obviously, because of different masses, and you apply a different amount of energy to them. The same amount of energy to them. They're going to react differently. One's going to go faster. The lighter one's going to go faster and further. But what we do know in terms of friction is that, when you launch an object, when you give it motion, they're going to wind down to friction over time. As it runs along over time, that, it's going to lose its energy to friction. So in both cases, what we need to look for is the time. How long does it take in terms of time for each object from its launch to its coming to a standstill? How long does it take? And that'll give us a good indication, because we know they've got the same energy in. So obviously if we see discrepancies in the time, you know, one's vastly shorter than the other, then clearly the energy is being sapped out at a different rate. So, right, I think it'd be good to launch the heavy mass first, you know, compressor spring, launch it, and take note from the moment it's launched to the moment it gives up all its energy, how long that takes, how long the time takes. So we launch the heavy mass, the 4 kilogram, and see how long it takes to wind down to friction. We'll do a couple of trials, well, maybe 3 or 4 trials of that, and then obviously we'll reduce the weight. So again, same cart, same low friction, same surface, same everything. Reduce the weight, launch it with the same spring, same amount of energy, and then obviously make note of the time it takes for that cart to wind down to friction. And then we look at the differences between the two, because we've got the same energy in. Obviously we would expect the same energy out, but if this is incurring more friction, or this is incurring less friction, however you want to say it, then there should be some, not saying significant, but there should be some discernible, you know, difference in time. That's, you know, out of the trial, say we do 4 of this one and 4 of this one, we should be seeing consistently lower, you know, lower times for the heavier mass and longer times for the lighter mass. So that's what we should see if what you're saying is true, you know. But again, you're making a claim, we can test these things, and that's what I'm proposing, that, you know, we test this out and see how these things function, rather than just, you know, while I'm drawing a picture here and you're very good at drawing pictures too, I'm actually going to move to, you know, some experimental setup to bolster what, you know, I'm not claiming anything here, I'm just showing the evidence. Luckily, this experiment's already been done by Stephen Bruff around about 9 months ago, so I don't have to go to the trouble of actually constructing it and building it and executing it, because Steve did a fantastic job of that already. You know, he did a very, very thoughtful, you know, plan on it. Obviously did a really good construction and executed it very well. So with his permission, I've edited some of the footage from that video, and as I've said previously, what we're looking for is the time. So we're going to launch, you know, we're going to show the heavy mass, the 4 kilogram mass being launched first. We've got to make note of the time it takes from the moment it's launched to the moment it comes to a standstill. That's the time we're looking for. And then obviously the weights, the 2 kilograms will be taken out, so it's now half the weight, released with the same energy, moving at 1.4 times the speed. So it is faster, it's lighter. That seems to be your claim. Faster, lighter objects incur less friction, or I say vice versa, heavier masses incur more friction. So again, when we launch the 2 kilogram, again, it's going to go faster, it's going to go further. In Steve's experiment, obviously, because, you know, he's launching this thing, and obviously doesn't have loads of room, so it makes sense just to launch it from one wall to another wall and just bounce it back and forth. We know springs conserve energy, so there's a spring on each end of the cart. Yes, it is going to hit, change direction, so on and so on, but each time it does that, the springs are very good at storing energy and returning energy. One of man's greatest inventions in that respect. So yeah, each cart's going to be launched, bounce, 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 and eventually it will come to a stop. It'll wind down to friction. Both carts will do that, and all we're interested in is the time, because we know the inputted energy is the same. So if the energy is being drawn out at a different rate dependent on its weight and its velocity, then we would expect to see, like I say, not necessarily significant, but if we do 4 trials of each, we're looking for a consistent difference in time, and that will let us know what's going on and whether your claim is true. So the footage I will be showing is courtesy of Stephen Bruff, who did a fantastic job. This video that he did actually was very underrated, very overlooked. Obviously he demonstrated the 1.4 thing very well, which clearly you don't accept, but there it is. That's the facts, whether you like it or not. And you're probably not going to like this fact as well when we show the footage and you see the results, but energy is not momentum. So now we're going to do the half the mass. It's going to 1.4 times faster speed wise. The 4 kilogram run was roughly 24 and a bit seconds. So if we're saying that this lighter, faster cart has some advantage in terms of not having its energy drawn out over friction, we could expect it to run for a longer time. So if the 4 kilogram cart was running for 24 and a bit seconds, I don't know, I mean, it's going 1.4 times faster, so did we say this run time is going to be 1.4 times longer? Obviously it's half the weight as well, so obviously that gives it an advantage. So we should be seeing a run time, if its energy isn't being drawn out through friction, because it's somehow because of its speed, it's getting a free ride to some degree. Then again, we should expect to see a longer run time. I think if we times this by 1.4, I don't know, would it be in the region of like 32, 30, 33 seconds maybe, I don't know, off the top of my head. So, you know, if it's going 1.4 times faster and that's its advantage, then, you know, we should be looking at a run time around this mark. So we'll run the test and see. Right, so having run the 2 kilogram cart, we can see that the times are almost identical. Like I say, somebody could probably do, you know, maybe Dispar could actually take Steve's original footage and do a frame count or something like that. I'm not able to do that. Like I say, I've just timed off a stopwatch. Probably not the most accurate, but, you know, for the purposes of this argument or presentation, or whatever you want to call it, it's pretty clear that, you know, each object, you know, regardless of its weight and its velocity is, what did we say, 10 for that and 14 for that. You know, so regardless of its weight and speed, the amount of energy going into both equals the same runtime for both. Same time, same energy in, and same energy out. No more, no less. So obviously the energy of this lighter, faster one is not getting a free ride, and the heavier, slower one isn't incurring more friction. You know, the same energy is going into both and the same energy is coming out. So friction's obviously being drawn out at a linear rate. Like I said, I will leave a link to Stephen's original footage and video. Like I say, it's worth a view. Very worth a view. It's a really good video, really good demonstration. If anyone wants to do a better timing and analysis, that'd be great. Like I say, I've just done it sort of a rough way, but, you know, maybe if you can load it into a computer and get the frame count, you could get it down. I mean, I think when I was timing it, the lighter, faster mass was a little bit, tiny little bit shorter in time, but that could have been, you know, I'm talking like points of a second, but, you know, that could have just been the way I'm timing it with a stopwatch. Like I say, if somebody wanted, if Dispar, you know, or somebody else wanted to analyse it, that'd be great, because it'd be interesting to know the exact, you know, times per run. But, you know, all in all, it's a pretty damn close thing. You know, the faster, lighter one and the slower, heavier one, given the same energy in both cases, equals pretty much the same energy on the way out. You know, friction for this one doesn't differ for this one. So in conclusion, you know, is friction linear? Yes, it appears to be.